All right, guys. So now we are doing your second lessons of your basics of calculus, right? So earlier we did the first lessons where we talked about very basic stuff like your domain, your range, your functions, right? And we try to have a deeper understanding of the definitions of your basic things, right? So very, very simple, very easy. We discussed a little bit about convexity also, concavity also. Now we are advancing. Now we are advancing to the next topic, which is a very important conceptual bridge in your quantitative finance, right? So you're doing the maths in quantitative finance and limits. Limits are the ideas that later become your derivatives, Greeks. Limits are the idea which tells you about instantaneous returns, your continuous time finance, your stochastic calculus, right? So everything originates from here, right? So try to teach it very intuitively, not like your formal maths class so that you understand, right? When you talk about your limits and continuity, please understand that in the previous class, we learned how your financial variables are represented using your function, right? Now we are asking a deeper question. What is that deeper question? How do these functions, how do these functions behave when input changes by extremely small amounts? Okay, this is the idea behind limits. Okay, this is the foundation of your calculus. Okay, so when you talk about your learning objectives, right? The next part, right? We talk about your learning objective. Please uh, note it down that by the end of this lesson, right, you will be able to understand the concept of a limit and its role in calculus. Right? When I say concept of a limit tells us what value a function approaches. What value a function, which we studied in the previous topic, what value a function approaches when the input gets very close to a particular number. Then we'll talk about evaluating limits. We'll talk about your evaluating limits. Evaluating limit means calculating the value that the function kind of approaches, even if it does not exactly reach it, right? Then you have the continuity. Continuity means the function changes smoothly without your sudden jumps. And why this matters in finance? Again, you have to understand each point with some kind of understanding here, right? So in financial markets, we often look at very small time changes, right? Very, very small time changes. For example, we look at return over a 1 second. We look at return over 1 millisecond. We can even look at return over 1 microsecond, right? So limits allow us to study returns as time approaches zero. This leads to your continuous compounding and your stochastic processes. Now, we also need to understand is that price behavior near your strike or barrier level, right? Option prices behave very differently near the strike price, right? This is what we need to understand. For example, I hope you have this understanding of your option prices. For example, if strike price is very close, if the stock price is very close to the strike price, your S and X are very close, option value becomes extremely sensitive, right? That's why we have Greeks, extremely sensitive. Limits helps us to understand this behavior. This later becomes your delta, this later becomes your gamma, and we need to look at your stability of your pricing model. What is the stability of the pricing model? Good financial model must behave smoothly. If a model jumps suddenly, it becomes kind of unreliable. Limits and continuity ensure models are kind of stable, right? Now, when we go ahead, right, when we look at uh, the concept of a limit, right, but when we try to understand this part, right, see, as I told you, right, limit describes what happens to a function when the input, what happens to a function when the input gets very close to a certain value. Mathematically, the relationship given is limit x tends to a, fx is equal to l. Right? This means that as x gets arbitrarily close to a, the function value fx approaches your l, right? So meaning x gets very close to a, the function approaches l. Now, what is the key idea here? So the key idea here is the function does not need to equal your L exactly. It only needs to approach L. Function doesn't need to equal L exactly. it only needs to approach L, right? And this idea is very powerful, right? For example, simple example I'll give you, right? Let's say our function is fx is equal to 2x plus 1. What happens when x approaches 2? Right? What happens when x approaches 3? See, if x approaches 3, fx will become what? Fx will be 7, right? You will say that if x approaches 3, right? If x approaches 3, fx becomes 7, right? Makes sense, right? Now, as x get closer to 3, even if you have x 2.9, fx is equal to 6.8, 2.99, 6.98, 2.999, 6.998, right? The function approaches 7. So the limit is, right, limit x approaches 3, fx equals 7. Now, what is the takeaway here is that what the student you need to understand is that limits describe the behavior around a point. Limit describe the behavior around a point, not necessarily at that exact point. Okay, the value at x is equal to a may or may not exist. The value at x is equal to a may or may not exist, but the limit can still exist, right? So the financial intuition which you need to build here is that whenever we are thinking about returns over very small interval, right? So consider your stock price, let's say ST, right? The stock price ST. Now, if I have to take return over a very tiny interval, I'll say that it is ST plus that delta T small interval minus your ST divided by your delta T, right? So now imagine when T tends to 0, right? Okay, this limits becomes the instantaneous return, right? This is the foundation of your continuous time finance models. And we look at your option behavior near your expiry also in this way, right? What is the option behavior near expiry now? That's the second thing. I've already told you about small time interval. See, when think about option behavior near expiry, as time approaches your expiry, what will happen is T will become equal to T. As time approaches expiry, T will. So option price behavior changes rapidly. Limits help you analyze this. So your Greeks, which play a very important role. I hope you know a little bit of finance, but Greeks play a very important role. If you don't know, at least note it down. Right? This is how your trader study your expiry effects, right? You must have seen that market becomes very volatile near expiry, right? So that is what you need to understand. Okay. Now, next part is that we are trying to understand, we're trying to evaluate. We're trying to evaluate limit. There is a method called direct substitution. First, we need to understand the simplest of case, right? Which is sometimes limit are easy to capture. We simply plug the function or plug the value into the function. For example, fx is equal to 2x plus 3, which I told you, 2x plus 3 becomes 7. So very, very simple. X tends to 2, we have taken, right? So when does direct substitution works? Direct substitution works when function is continuous, right? Function is continuous. What does function is continuous means? Continuous means graph has no jumps. Okay. Then expression is defined, right? No division by 0 or undefined expression. Expression is defined. Expression defined means no division by 0, because you know anything divided by 0 doesn't fetch you anything, right? It is undefinable, right? And no undefined expression, right? Now, if you try to do the financial interpretation of this, right? In finance, this corresponds to a smoother price behavior, right? So, for example, if stock price moves from, let's say, 100 to 101, 101 to 102, right? The change is kind of smooth, right? The model assume this kind of behavior. This is why in many models, we assume continuous price movements, right? So if you are a quant who is operating in the quantitative world, and you are looking at quantitative frameworks, right? Limits lead directly to the most important concept in quant finance, your derivatives, right? Sensitivity of price to a variable. For example, you will see ahead, right? I'm not covering it right now, but you will see ahead something called delta. Delta is the change in the call option price or put option price, the change in the corresponding change in the stock price on the underlying. This measures how your option price changes as the stock price changes. Then we use continuous compounding also. Continuous compounding, you know that you've seen the previous chapter. Your continuous compounding is what? A is equal to E exponential ERT, right? So this comes from your compounding frequency, which is approaching infinity. Then also we use something like in Black-Scholes model also, right? We use in Black-Scholes model also. Stock price assumed to follow your continuous motion. This assumption relies on your limit concepts. Okay. So overall, in this first four slide, we have tried to understand limits. Limits helps us to understand how your financial variable behaves, when changes become extremely small. And this idea leads to your derivative, your sensitivities, your option Greeks, which will come ahead, right? Don't worry about it. And stochastic calculus, which you need to understand. Without limits, modern quantitative finance cannot exist, right? That is why we are studying it, right? So remember that. We are covering the basics, which you have to know. Okay. All right. Now we are going to the next part, right? So this part, right? Please understand. This part is where students usually get confused. So I'm trying to, or I'll try to explain it in a very structural approach, right? Step by step, so you are able to understand, right? First, we talk about your indeterminate forms and your algebraic explanation, right? When I talk about indeterminate forms and algebraic manipulation, what we need to know is that sometimes when we substitute the value directly into the function, while calculating a limit, we get something like 0 by 0. Okay, this is called your indeterminate form, right? So 0 by 0, please understand, is not equal to 0, right? 0 by 0, please understand, it is, some people think 0 by 0 is equal to 0. No, 0 by 0 is also not equal to infinity, right? It simply means the expression needs further simplification. If I have example, fx is equal to x square minus 1 divided by x minus 1, right? And you are given like find if limit x tends to 1, right? So first one is a direct substitution, right? If you do the direct substitution, right? Let's say you do the direct substitution here. If I do the direct substitution here, I will get what? 1 square minus 1, 1 minus 1, which is 0 by 0, right? Which is wrong, right? Which we can't use, right? This is an indeterminate form. Right? So how do we solve this? To solve this, we have something called algebraic manipulation, right? So what we do is, algebraic manipulation, which is fx is equal to x minus 1 divided into x plus 1 divided by x minus 1. So basically we are factorizing x square minus 1 for x not equal to 1, right? You are seeing fx, x minus 1 gets cut, x equal to 1, limit f x tends to 1, fx is equal to 2, right? So what we are trying to understand is that exactly x is equal to 1, right? See, we have taken for x not equal to 1. Exactly at x is equal to 1. So at x is equal to 1. Exactly. X equal to 1, right? Function is indeterminate. We get your 0 by 0 form, right? Which is indeterminate form, right? So at x, exactly at x is equal to 1, the function is kind of undefined, but the limit still exists. This means the graph has a kind of hole, right? It has a gap at that particular point. If you think about this financial intuition, sometimes your financial models look unstable at first glance. Example, your transaction cost models. Initial formula may look very complicated or undefined at a point, but after simplification, the behavior becomes kind of smooth. And this happens frequently in your liquidity model. This happens frequently in your microstructure model. This happens frequently in your option pricing approximation, right? Which we need to understand, right? Something which can look very unstable at first go, if you simplify it, can become very easy to understand. Okay. Then we have your infinite limits, right? Again, we are introducing a very important concept here. An infinite limit occurs when the function grows without your bound. Mathematically, what we get is limit x tends to a fx. Limit x tends to a fx is equal to infinity. This means the function becomes extremely large. This means the function becomes extremely large. For example, right, we have fx is equal to 1 by x, and limit x tends to 0, right? The function becomes infinite, right? So as x approaches 0 from the positive side, let's say x equals 0.1, fx becomes your 1 by 10. If x becomes 0.01, right, fx will become what? 100. If x becomes more smaller, 0.001, fx becomes 1000. The value becomes larger and larger as we move from the positive side to the towards 0, right? So limit x tends to 0, fx is equal to infinite. Graphical intuition which have been given here, right? Graphical intuition. Please understand now x is equal to 0, the function shoots upward, the line x equal to 0 becomes a vertical asymptote, right? Becomes a vertical asymptote, right? Now, what is the financial interpretation here, right? Financial interpretation is that this concept will appear everywhere in your finance, whether you're studying your leverage ratio. Leverage ratio is what? Your debt by equity. E by E, right? Debt by equity. If equity approaches 0, right? If equity approaches 0, the leverage kind of explodes, right? There's a risk near default. When a firm approaches your bankruptcy, risk measure increases sharply. Trade spreads kind of explode. This behavior resembles an infinite limit, right? Okay, so that is what we need to understand. Okay, then once we have done this, we move to the next part, which is your one-sided limits. Okay, to talk about one-sided limits, what is happening here is that many financial functions behave differently depending on the direction from which they approach the point. Okay, please understand. Many financial functions behave differently. They follow different rules, right? Depending on the direction from which they approach a point. So direction is also very important, right? So we define two limits, right? One is a left-hand limit, one is a right-hand limit, right? Because from which side you approach, that is very important as well. So if you are approaching from the left, right, x tends to a minus fx. And if you're approaching from the right, x tends from a plus, right, fx, right? So now you have a continuity condition. What's a continuity condition, guys? Okay, so continuity condition basically means a function is continuous at x is equal to a if left limit exists, right limit exists, both limits are kind of equal. Okay, continuity condition means left limit exists, right limit exists, and both limits are kind of equal. They equal the functional value fa, right? So when your limit x tends to a minus 1, fx is equal to limit x tends to a plus fx is equal to fa. That is your continuity condition. And why your one-sided kind of limits matter in finance? Because many financial institutions are piecewise function. We have seen what is a piecewise function, right? So like your option payoffs, your tax structure, your transaction costs, different formula apply in your different regions, right? So in that case, right, we want that your we can use some one-sided limits. So price or payoff must behave smoothly around critical values, strike price for stable pricing, and that is why one-sided limits work great, because sometimes we have a limitation, right? Sometimes you have a limitation, and that limitation it has to be honored, right? That can't be honored in the two-side limit. That can only be honored in the one-side limit, and that's why it helps. Okay, especially in option payoff, because option payoff is only one-sided, right? You know that for greater than like call option payoff, we have seen, right? If the stock price is greater than strike price, if it goes above, you get a payoff, right? If it goes below, that's a zero payoff, right? Limit x, you've seen the previous chapter, right? Option payoff, piecewise function. Go back and revise that if there is any doubt, right? Okay. Same thing. Okay, great. I thought you can go back and revise, but it is given here, right? This is what I was talking about. This is given in your previous chapter also. European call payoff, option payoff. If ST is less than K, it is 0. ST greater than K, it is greater than or equal to K, ST minus K, right? So one-sided limit at ST equal to K, right? limit st tends to k minus 1, fst is equal to 0. Limit st to k plus 1, fst is equal to 0, right? So function value fk is equal to 0, right? A function value fk is equal to 0. And then what is happening here, right? See, we are looking at behavior near your strike price. So let your st tends to k, right? From left side, we have seen st tends to k minus 1, k minus. So fst is 0. When st tends to k plus, fst is 0. Now, again, the idea is, right, when stock price approaches strike from above, when stock price approaches your strike from above, right? When stock price approaches, what are we getting? What will happen here is that, let me write it here. What will happen here is fst is equal to st minus k, right? At st is equal to k, because k is given, right? St is equal to k. At st is equal to k, right? What will happen? See, we are approaching from the right side, right? We are approaching from the right side. When we are approaching from the right side, right, st is equal to k, right? So it is k minus k, na? So it becomes what? K minus k is equal to 0, right? So limit st tends to k plus 1 is also 0. Limit st tends to k minus 1 is also 0, right? So function value at st is equal to k. And so at st, at your st is equal to k, fk is equal to 0. Okay. So limit st tends to k minus fst is equal to, so what are we getting here? This is the relationship given. Limit st tends to k minus 1, fst is equal to limit st tends to k plus 1, fst is equal to fk, right? Therefore, the payoff function is continuous at the strike price, right? What is the important insight we have to take away from here is that although the payoff is kind of continuous, right? Although the payoff is kind of continuous, the slope changes drastically. The slope changes sharply at the strike. At this point, the slope is changing, right? This leads to your option delta change. This leads to your large gamma near strike, right? If you don't know delta gamma, hold on, right? Hold on. If you already know, you will understand. If you don't know, it will cover here, right? So, which is why traders closely watch your ATM options, right? Add the money option. If you don't know concept of add the money, don't worry, it will come ahead, right? Add the money option, right? So you have to understand this. See, guys, you are learning your maths and quantitative finance, but I have to join the concepts with the financial concepts, right? You might not know them right now, head they will be covered, but that is why traders choose or closely watch ATM options, right? So this is a financial concept. I'm trying to join the dots, right? So limits helps us understand how financial variables behave near your critical points like your strike price, your bankruptcy level, your expiry dates, your leverage thresholds, right? This is why limits are the mathematical backbone of your quantitative finance, which we need to understand. Okay. All right. Then we go into your definition of continuity, right? Although we covered continuity function, but a function is continuous if the graph can be drawn without lifting your pen, right? It's very simple, continuous without lifting your pen. That means there are no jumps, there are no breaks. And when you look at the definition of continuity, a function is continuous if all three conditions below are satisfied. The function fa is defined, the function value kind of exists. This means the function is defined at that point. Limit x tends to a, fx exists, the limit exists, meaning the function approaches a specific value as gets close to. Condition number 3, limit x tends to a, fx, fa, the limit equals the function value. If all three conditions hold, the function is kind of continuous. When your discontinuity occurs, when does your discontinuity occurs? Any one condition kind of fails, the function becomes kind of discontinuous. This means the graph has your jump, graph has a hole, graph has a vertical break, And if you look at your applications in finance, what you need to understand is that there is a jump risk, right? What is the jump risk? That in real market, prices sometimes jump suddenly. For example, a major news announcement, a central bank decision, a geopolitical shock. These creates your price discontinuity. Models that assume your continuous prices may fail in such conditions, right? So then you also have your sudden drops in bond price due to credit event or defaults. So suppose a company defaults or a country defaults, right? Bond price might drop instantly from 100 to 30. This is a discontinuous price movement. And then we also look at your binary or digital option payoff, binary option and payoff, 0 or 1. For example, if price is greater than your strike, payoff is 1. If price is less than strike, right, the payoff is 0, right? Binary option, the payoff is only 1 and 0, right? If you're above the strike, you get full price. If below the strike, you get 0 price. It's not like normal call or put options, right? So the payoff jumps suddenly at the strike, right? This is a discontinuous function, right? So the overall, the key idea here is that most pricing models, most pricing models assume your continuous or continuity because it makes your mathematics tractable, but real markets sometimes contain your discontinuity. That is why advanced models include your jump processes, and that is why we need to understand. Okay. All right. Then we go into your next part, which is you're trying to understand your jump and sharp corners, and you are trying to get the graphical insight. So now we are trying to explain how graphs help identify your discontinuities. If you look at the visual inspection of your graphs, it helps detect your two structures, right? When you look at jumps, jumps are what? Jumps are basically a jump occurs when the function suddenly changes value, right? So there is a kind of a discontinuity, right? Suddenly changes value. That is a kind of jump occurs when the function suddenly changes value, right? When the function kind of jumps, right? So there is a discontinuity, right? When function kind of jumps, right? Please understand that left limit is not equal to right limit. Okay, so function is kind of discontinuous. Then we talk about your sharp corners. Sharp corners are non-differentiable points. Sometimes the function is continuous, but the slope changes suddenly, right? Abruptly. This creates a corner, right? This function is continuous, but not differentiable. Continuous, but not differentiable. Okay. Now, when you try to look at the financial interpretation, please note here jumps. The example include your dividend payments, your credit default events, your uh, binary option payments or payoffs. This creates your sudden price changes. When you look at your corners, option payoff functions have corners at the strike. For a call option, we know what is the payoff, right? And also we know that the slope changes suddenly. Below strike, the slope is 0, right? Which is here. Above strike, the slope suddenly becomes 1. This sharp change creates a corner, right? So this is the kind of corner we are talking about, right? What is the important uh, trading insight we can get here is that, see, because of this corner, right, which we are getting at the strike price here, right, option delta changes abruptly near the strike, which is this strike price, right? That is why trader monitor your ATM options carefully, right? Jump, you have understood, right? This is a jump, right? There is discontinuity in the price. Okay. All right. Then we look at your asymptotes and your infinite limits. So we're trying to introduce your asymptote. Asymptote is a line that the function approaches but never touches. Asymptote is a line which a function approaches but never touches. Now, what is the vertical asymptote? Vertical asymptote occurs when the function becomes extremely large, right? So again, the value is limit x tends to a, fx is equal to infinity, meaning that the function grows without bound near that point, and x tends to a, right? It is, you see, x tends to a, this point. You see, it is not touching it. Even if I take this point ahead, right? It is getting infinite, but it's not touching it. It's getting closer and closer, but not touching it, right? So vertical line becomes like a vertical asymptote, right? Now, why are we studying it? What is the financial interpretation here? Uh, this behavior appears in your several financial situations, your leverage explosion. We know the leverage ratio. Leverage ratio is debt by equity. So as equity tends to zero, it explodes. All right. The leverage became extremely large. This resembles a vertical asymptote. The risk near default. The risk near default. When a firm approaches your bankruptcy, firm approaches your risk measure kind of explode. Credit spreads rise sharply, volatility kind of spikes. This resembles your asymptotic behavior, right? That is what we need to understand. Okay, asymptotic behavior. Okay, that is what we need to understand. Okay, all right. Then we go to financial meaning of asymptotes. Easy slide, guys. When we talk about financial meaning of asymptote, please understand that in finance, asymptotes signal your extreme instability. They warn us that small changes in your inputs can produce huge effects. So where it is used in finance, we have default probability models. When leverage kind of increases, default probability increases very, very sharply. Near your distress level, risk matrix grows rapidly. Then we have your leverage ratios. When equity becomes very, very small, leverage explodes, that is equal to 100, equity is equal to 10, leverage becomes 10, right? When equity is equal to 1, leverage becomes 100, equity is equal to 0.1, leverage becomes 1000. This resembles, again, an infinite limit. Then we have risk measures. Some financial risk metrics become extremely large near your crisis situations, right? For example, your volatility spikes, which happen whenever there is geopolitical tension, etc. Right? Margin requirements kind of explode also when there is a risk measure and we are near the crisis situation. War increases rapidly. So the key idea here is the key insight which you have to take away is that asymptotic behavior warns us that financial systems can become unstable very, very quickly. Small changes in your inputs can cause your massive financial consequences. That is why risk managers should monitor your variables that approach your critical threshold, right? Risk manager should monitor the variables when they approach the critical threshold, and that's why the critical threshold has to be understood properly. Okay. Overall, if I kind of summarize, right, last 3-4 slides, we are trying to understand how functions behave near your critical points, right? Continuity ensures smooth behavioral models. Discontinuities indicate your jumps and shocks. Asymptotes warn about your extreme financial instability. These ideas form the foundation for the next topic which will come ahead, right? Which we'll try to understand. All right, now we have questions. What happened to price as time approaches maturity, right? So we are looking at your limits in the financial price models, right? So limits are extremely useful in finance. We know that already because many financial quantities change continuously over time. So we need to understand limit. Now, what happens to bond price as time approaches maturity? You consider a zero coupon bond price, right? Zero coupon bond means that there are no coupon payments, right? Only one payment at maturity. So face value is kind of 1. Then the bond price formula PT is equal to exponential minus RT minus T, where R is the interest rate, T is the maturity time, small t is your current time. So what happens to price the time approaching maturity? So basically, we are saying that when T tends to T, small t tends to big T, basically what we are doing, if T is tending to T, which means that T minus T is tending to 0. So it is, if you put the thing, right, exponential is 0, we get almost 1, right? So if we substitute the value exponential 0, is anything raised to power 0 is 1, right? So limit tends to T, your price tends to 1, right? Now, what is the financial meaning of this, which is very important to understand? That as maturity approaches, the bond price converges to its face value, right? The face value that we need to understand at your 100 rupee bond near your maturity, price becomes like 100. That is why bonds always converge to par at the maturity, that we need to understand. Okay. Then we go to the next point, right, which is your what happens to return for your small price changes. Again, now we're asking a very interesting question, that what happens to return? What happens to your return, right, when price changes become very small? Again, see, the formula is R equal to P1 minus P naught upon P naught, right? So let price changes be very small, right? P1 is equal to P naught plus H. Then H is a small change. R is equal to H by P naught. And then let's take the limit H tends to 0. R, as H tends to 0, R also becomes 0, right? So very simple. What is the financial meaning of such thing? See, we try to interpret the financial meaning of such thing. If price become extremely small, the return also become extremely small. Why this matter? Because this idea leads to your instantaneous return in your continuous finance, right? This becomes the basis of your what? The stochastic model, your Black-Scholes model, the geometric Brownian motion, all those things, right? So instantaneous return concept comes from here when limit h tends to 0, r is equal to 0. Okay. All right. Then we go to next part is a European call option or call payoff continuous. So we are again visiting, or in fact revisiting, the European call option payoff. C is equal to max st minus k comma 0. We have seen it in the previous chapter also, this chapter also. Piecewise, it is this form, right? C is equal to 0, st less than k is 0, st greater than k is like this. So is the payoff continuous at the strike? So if you take the left hand limit, right, st tends to k minus 1, payoff C to 0. We take the right hand limit, right? Right hand limit if we take, so what happens here is C is equal to st minus k. See, left hand limit, it is direct, right? It is coming directly from here. Right hand side, what I'm trying to say, right hand limit. Right, C is equal to st minus k at your st is equal to k. St is equal to k. K minus k becomes 0. Right, k minus k becomes 0. Right? Okay, so limit st tends to k minus 1, c is equal to 0. Limit st tends to k plus 1, c is equal to 0, right? So ck is equal to 0. Okay, the payoff is continuous at the strike, but the important insight or important thing you have to realize here is very, very importantly that the payoff is not at the strike. There is a kink, right, which we need to understand. Kink we have seen now, right? Below strike, slope is 0. Above strike, slope is 1. This sharp changes causes your, in the financial world, it causes gamma spikes near a strike, heavy trading in your ATM options. That is why it's so popular, right? Then we go to what happens as compounding frequency increases. See, again, we are trying to introduce one of the most famous limits in finance. That is your future value with compounding n times per year. Future value is equal to 1 plus r divided by n raised to t. As limits n tends to infinity, right? So what happens? Your compounding becomes extremely frequent. N tends to infinity. So limit n tends to infinity, 1 plus rt nt. So, ultimately we are getting ERT, right? And why? Because you understand, right? If n tends to infinity, right? Whatever is r, right? R by n will obviously turn into your 0, right? So it is your 1 plus 0, 1 nt, right? Or if n tends to infinity, right? What is happening here is, if compounding becomes continuous, we obtain the continuous compounding formula, right? Why? How are we getting exponential RT here? Limit n tends to infinity, right? See, we have 1 plus r. N is very large, right? N is very large, right? And here also n is very large, right? Here also n is very large, right? N is very large, n into t, right? So please understand, the effect of n comes here also. Effect of n comes here also. Right? Then we get exponential RT, right? You don't need to derive it, just remember it. Right? If you understand, right? This is your exponential RT, because in simple words, you also understand that compounding is when you add, you know, when you multiply, or when, see, one function is linear function when you add the constant amount to each other, right? One is compounding, right, which is different from adding same amount each year, right? Now, when you look, and we have seen this exponential function earlier, right, in the previous chapter, right? So in your financial modeling, when compounding becomes kind of continuous, we get your continuous compounding. It is used in your bond pricing, it is used in your option pricing, it is used in derivative pricing, derivative model, your discounting formula, etc. Right? So remember that. Last but not the least, we have question number 5 is portfolio value continuous. We are looking at continuity in portfolio values. Portfolio value formula VS equal W1 S1 W2 S2. We saw in the previous chapter where S1 S2 are the asset prices, W1 W2 are the portfolio weights. Now we are trying to ask, is portfolio value continuous? Yes, because it's a linear function of your asset prices, which is this, right? If asset prices are continuous S1 S2, then portfolio value is also continuous. So that is the condition, right? And you take limit s tends to a vs, it becomes va, right? Now, what is the financial meaning of this? Small changes in your asset prices lead to small changes in your portfolio value, and this is extremely important in your risk management, where portfolio risk models assume smooth price behavior, right? It is very important in your delta hedging, right? Option hedging relies on your small price movement, right? It is also useful in your sensitivity analysis. Measures like your delta, gamma, vega requires smooth relationship. So overall, what you need to understand is in this chapter that limits and continuity explain how your financial variable behaves near your critical points. Bond prices converges to face value, returns vanish for very tiny price movements. Option payoff continuous but kinked, right? Compounding becomes exponential. Portfolio values give out your smooth functions. These concepts form the mathematical foundation for derivatives, for your option Greeks, your continuous time finance, your stochastic calculus, all those things, right? So that is what we are looking for, right? And with this, we complete this lesson number 2, right? We have more lessons coming your way, guys, but I hope you understood. Go back, revise it. It's not that difficult, but it's a very vital kind of concept, right? We have covered only 2 topics here, limits and continuity. I tried to give you examples also where limit and continuity are used in the world of finance, so remember that as well. Concept of limit, direct substitution, indeterminate form, then what do we do? Algebraic manipulation we have to do, then infinite limits, what do we do there? Right, one-sided limits, why they're important, call option payoff, definition of continuity, what are the 3 conditions for your continuity, right? We have then jumps and sharp corners, what do they mean, right? Asymptotes and infinite limits, financial meaning of asymptotes, then questions, what happened to price at time approaches maturity, what happens to return for small price changes, how does the European call payoff in the continuous form, what happens if compounding frequency increases, and finally, is the portfolio value kind of continuous or not, okay? All right, guys, with this, we have completed lesson number 2. I'll see you in lesson number 3. Okay. All right, guys. Thank you.